Let's go. All right, welcome everyone, and to this weekly community call about ElScript, using ElScript to program Bitcoin smart contracts. So last time we introduced this primitive called elliptic curve cryptography. So basically we define just want to a brief overview, a review. So we'll talk about elliptic curve are usually defined by this equation and on some kind of a field, or you can think about real numbers. And we define a few primitive operations such as addition, doubling, and also scalar multiplication. So with that, we also show one example where it could be useful, right? We can just using this primitive, basically addition, point addition and scalar multiplication to re-implement the so-called Bitcoin signature verification, which has, can enable to sign arbitrary message. That's just one very obvious advantage. So in today's talk, I'm going to cover more use cases, which I think is all very cool. And based on this seemingly simple primitive, you can derive a lot of more advanced cryptography algorithm. I implemented them and then use them in a smart contract. Okay. So the first one I'm going to show you today is so-called Schnorr signature. So just before I even started, so anybody who have heard about this term before? Schnorr signatures?
Heard about it some time ago, but to be honest, I don't remember anything.
No worries. I think that this is mostly, hyped by the BTC chain, right? Because they argue, hey, we have the ECDSA signature scheme, but it's not as good as the Schnorr signature, right? One of the big difference here is, Schnorr signature basically is a different signature from ECDSA, which is used by default in Bitcoin, right? When you do the check sig, okay, natively. So one of the so-called difference is, for example, let's say you have 3 inputs, right, from 3 different senders. Oh, okay, let's say this is inputs, right, and this is these are the inputs from different senders. So if it's in one Bitcoin transaction, you have 3 inputs coming from 3 different senders. So each of them has to sign, right? And then this signature takes some space in the inputs, right? So that's what usually the ECDSA signature works, right? So if you have 3 senders, inputs, and then you need to add 3 signatures, which is okay, but compared to Schnorr signature, the Schnorr signature has this property is mathematical is called linear. So basically, if you have 3 signatures or even n signatures, if you add all of the signatures, it's actually still a valid signature against the sum of all public keys added together. Okay, so that's why the BTC chain proposed it, and then so they can so-called aggregate the signatures together. So for example, here, if you have 3 inputs, right? So instead of having 3 signatures separately, you can actually aggregate into one. And if this one signature verifies against the 3-1, it's going to be valid. All 3 signatures are valid. Okay, make sense so far?
Yeah, thanks.
Okay. All right, so let's keep going. So here, I just show you, it's just a different signature scheme, and this is also the how do you verify it, right? So again, it's like any other signature scheme. So you have a signature, you have public key, and you have the message. Okay, so this is the algorithm, how you verify it. So you can see the important thing here, you don't have to get all the mathematical details, but in this verification algorithm, similar to ECDSA, you have the primitive, scalar multiplication. You can multiply a point with a scalar, and also you can do, addition as well. So basically, thanks to the primitives we had before, so it's very easy. You just, once you import the elliptic curve, which already implemented, you just, even count all the spaces and comments is less than 30 lines of code. So it's very powerful, right? So instead of, having breaking changes in taproot and to introduce Schnorr signature, you can just, once you have the basic primitives, you can just code it in less than, I think probably less than 20 lines of code. Okay. This just gives you a sense why we, want to, I think the elliptic curve cryptography, the primitive is very important, because once you have these primitives, it's almost, that's, almost unlimited ways you can leverage, because this is a very basic primitive in cryptography. Okay. Any other questions? Schnorr? It's clear? Okay.
Yeah.
All right, good. So let's talk about another one. Again, it's another signature scheme. It's called ring signatures. So even before, okay, anybody has heard about this term before? Or called group signatures sometimes. Anyone? Okay, no problem. And basic idea is also very simple. So instead of a sign against a individual key, you sign against a group of keys. This group usually is you can form is in a ring. For example, here you have, let's say 5 people. Right? I beg your pardon? Okay, let's keep going. So instead of having one public key, you instead have a group of keys. Okay, so if any of these people in the ring are in a group sign, and you check it against a group key, it's going to be valid also. But anybody else outside of the ring, you can think of it, if they sign, you will check, the check will fail. Okay. So basically you have, let's say 5 people, right? So you can do some math about the public key. You can kind of add them together in a sense. Then you give it a group key. And then if any of them who can sign and then check against the group key, it's going to be valid. Any of them. So if you only look at the signature, that's one of the biggest features about so-called ring signature. So if you only look at the signature on which is usually probably on chain in the blockchain's context, you cannot tell which of this signed, because any of this can sign, right? So that is different from ECDSA, right? So if you know somebody's public key and you know the person's identity, and you see a signature and it checks out against that public key, it should come from the person that signs, right? Instead of here, you are hiding in a crowd. Make sense?
Okay. Yes.
All right. So this is, the first, I think the most prominent example would be, it's going to be, is in the so-called Monero chain. That's what it's really about. And again, you probably have guessed, yeah, it's the same scheme again, because this is all based on elliptic curve. So for example, here, I show how do you verify a ring signature against, its group public key. So basically, we don't have to go into all the details, but you have signature, you have a message, and you have the list of public keys. So this is a group of keys, right? So you can check with the 3, you can check whether this signature is correct, is within this ring. Okay, used in one of the person in the ring. Okay, so basically this is an algorithm. So the important thing, I think we don't have to, know everything, but here this is a hash, right? We can, of course, we can simply do, and then the important thing is this equation here. So you see, this is the capital letters, they represent points. So if you have a lowercase, that's a scalar multiplication, right? And this is scalar multiplication. And then when you add, this is point addition. So you can basically once you have this, we have all the primitives, right? Addition and then scalar multiplication. And of course we have hash. So we can also implement this easily by just, coding this up. I think usually in maybe 20 lines of code or even 30. Okay. So you can actually implement the ring signatures. But the important thing here is you don't have to launch another blockchain or have breaking changes, okay, to implement that. You can implement this on top of Bitcoin using the smart contract. All right. Any question regarding ring signature or group signatures?
One question, so this can be actually used to in a smart contract, I guess, to get like 3 out of 5 signatures or something like that, right? So when you need a number of different signatures by different people.
Yeah, that's a different scenario. You are talking about so-called multi-sig. Okay, so ring sig is just one person signs. Okay, one person signs. If it's within the ring, you will check out the signature can be very validated. Okay, so it's just one out of, let's say, 5. But if you really want to do 3, I know that's a different scenario. Then you have to use so-called multi-sig. So it's a different signature scheme.
Yeah, can you use this 3 times and making sure that providing that
it
verifies it 3 times and
yeah. For that, yes, of course. So you are like simulating the multi-sig but using the ring sig. Yeah, of course, yes, as a interesting idea. But efficiency wise, it may not be as efficient as the native one because you already have a native one. But you may think of cases where you have this scenario, right? Of course. And then another thing you have to make sure is, hey, you have to make sure I don't think you can do that. So, okay, because let me explain. So let's say you run this, you have 5 people in the group, right? And then you run it 3 verifications and they all pass, right? But here's the thing. You may be signed by the same person 3 times. You see what I mean? Because you cannot tell whether they're different.
No, but the signature will be the same every time, right?
No. So again, it's like easy to say. It's not. I think it's not deterministic. Basically, you have the nonce, right? You have the nonce. But I have to double check. Yeah, I have to double check whether you have the nonce. Yeah, it may not. It's not deterministic. Yeah.
Yeah.
Okay.
I think I get your point. Thanks.
There may be a way around this to check whether the one person has signed multiple times. Yeah, if you're really interested, I think I'm going to put something in the show notes. Basically, I think it's called linkable ring signatures. Basically, it's going to say, hey, whether this is from the same person. Right? It's called linkable ring signature in the literature. So basically, some schemes, enhanced versions, and then if one person signs a signature and then sign another one, you can detect whether you don't know who signed, but you can tell if this is the same person. If you have 2 re-signatures, there are schemes like this. Okay, that can probably solve your problem. Basically, you have a multiple signatures. You run re-signatures multiple rounds, and then you check whether there are distinct private keys. Okay. Yeah, it's called linkable ring signatures if you want to dive into the details. Okay.
We'll check. Thanks.
Okay. Good question. Any other question? Okay. If not, let's keep going. All right. Okay. This is one of my favorite. I think, this is my favorite. Okay. Elliptic curve cryptography application. Okay. So anybody has iPhone or Android here? Anybody who does not?
Yeah, Apple.
Yeah, iPhone, Android, anybody? Okay, I assume, probably
Apple,
everyone has a phone like this. Yeah, we're not here to debate which one's better, but anyway, pretty much everybody get a smartphone these days, and if you have used a smartphone, you probably have used this biometric features, right? For example, you use Face ID, your fingerprints, to unlock, just for added security, right? So this, on all the modern phones, based either on iOS or Android, you have this, hardware component called secure enclaves. So that's where the magic, the cryptography, the math happens. Basically, what it does is it stores your biometric information, right? When you set up your iPhone, you put your face, you scan your face or scan your fingerprints. All the sensitive, right, biometric information is stored here. Okay, so yeah, we don't have to get into the hardware detail, but the important feature here is this thing is a separate component that's usually unaccessible to the CPU. Okay, so your program, when you have your apps running your phone, you cannot direct access here. You cannot, let's say, read the biometric information directly. Okay, it's isolated, so you can only do a very limited primitives. Okay, so basically two things you can think of. One, you do encryption. Okay, so you cannot get the raw data here. Basically, what I'm saying is it's impossible for your app, even it's malicious, because of the hardware design. So the chip does not allow you, it's not exposed. You cannot read the raw data, let's say fingerprint or your facial data, okay? Because it's very sensitive, right? If that is the case, somebody can have some malicious code and then, steal your biometric data, okay? So just for us, it's just to know, okay, you cannot access it directly. You can only do two things using the biometric data here. One, encryption. I think we don't worry about it this time for this scenario. And second, for signature, okay? So basically you can, once it generates keys, you can ask it, hey, can you sign on my behalf? And then if you, when you ask it to sign, you have to use biometrics to validate, to verify, right? Either your head, either your fingerprints or your face. Okay, so that's why a lot of sensitive apps, they use this kind of a secure enclave to secure the application data, or authorize, for, let's say, some kind of banking app use this to transfer data. You have to use, let's say, face data. Okay, is this clear? I think maybe people have not heard about this. Any questions about the secure enclave on these devices? Yeah, any question? Yeah, no question is dummy. Anyone? Okay, seems you guys all get it, so that's good. Okay, so with this magic hardware, so let's code some smart contract. The amazing thing is, you can turn your iPhone or Android into a wallet, a Bitcoin wallet, as secure as so-called hardware wallet. Okay, so when you sign here, nobody can get expose your private key. Nobody, not even the apps. They don't know your secret key, and somehow they can still sign, right? Because normally, if you store this on the device, let's say when you ask to sign, you have to use the private key, right? And then whenever you use private key, there's always security vulnerability, because the apps may steal it, right? Maybe malicious or some third party website or app. Yeah, it's not secure, right? And that's why people use offline hardware wallet. So they can turn literally your iPhone into a hardware wallet, our Bitcoin wallet, as secure as hardware wallet. Okay, let's dive into details. So, but this is what this smart contract can do. Okay, so before we do that, let's review a little bit concept here. So at the very beginning of last session, right, we talked about elliptic curves, right? So basically it's defined by this equation. It may look like something like this. Okay, so we talk about, because this is the family of curves. So depending on what your A and B is, it gives you different curve, right? So for Bitcoin, right? We use this curve called SECP256K1. Right? Basically, it's using this parameter. A is 0 and B is 7. Okay, that's the so-called Bitcoin curve. Okay, here's the only problem. If this is if the iPhone or Android already have this support this curve, right? The signature scheme on this curve, then we are done, right? We don't need anything else. We can pretty much just use the check the signatures, the ECDSA, the default one, right? And then we are done, right? We don't have to do anything else. But here's a little bit bad news for you, okay? Because the current, at least as it stands today, the Android and iOS, they do not support the Bitcoin curve, okay? They only support the alternative, like a SECP256R1, okay? So instead of K, this is R. So basically K is like a, you can almost think of deterministic, basically it's a simple number, and R is supposed to be random, okay? But we can get into another big conspiracy, whether it's really random or chosen by some NSA guy. But anyway, that's another topic for another day. So basically for R, it has a different A and B, right? This is A, this is B, okay? So it's still elliptic, but it's a different curve, okay? But unfortunately, the Bitcoin native one is different, right? So that means, hey, I cannot just use the checksum out of the box. But the good news is for us, you kind of already guessed, right? Because thankfully we can have programmable SQL smart contract, so you can just ask the iPhone to sign it with this curve, and then you re-implement the ECDSA signature verification using the different curve, using this curve, because it's programmable, right? We can just recode the checksum by using a different curve, and then we are done. Okay. Cool. Any questions? So basically after this, basically the workflow is you still ask your iPhone to sign. But here's the thing, when you submit this to the Bitcoin blockchain, instead of the default checksum, you are going to swap out the checksum with this one. So your iPhone can sign amazingly. And it has added security level as secure as a hardware wallet because of the secure enclaves. Your private key never gets exposed. Make sense?
Yep.
I have a question. Is this script on the right just the verification algorithm for the R1?
Yes, because that's the only thing you need, right? Usually when you generate signature, it's off-chain. And for us, basically you lock your Bitcoin into this contract, and then you can ask your iPhone to sign it with a secure enclave. Even so, in that case, even your wallet app doesn't even know the secret key. It never exposed, so it's more secure, right? It's almost like an offline or off hardware wallet, security level wise. Does that answer the question? Yes or no?
Yes, that it's obvious now that now that I asked it.
Okay. Okay, cool. Any other question or comments? Okay, if no, okay, I will post for anybody either watching live here or so watch it offline later on. Yeah, this is still open. Nobody. I think it would be cool if somebody can, get some kind of demo to make this work in using a real phone. It would be very cool, and then submit some transactions on chain, and we'll see. Yeah, that would be a very cool demo. And also for anybody who is thinking about wallets, if you really want the ultimate security, yeah, you can use this contract, and then make sure, then we don't need some ledger or nano, whatever. We can just use your existing phone, and it will be as secure as a hardware wallet. That would be very cool. Okay, so this is just open challenge for anybody who wants to use this cool technology. Okay.
I do have one question about the. I do have one more question. Sorry.
Go ahead.
About the R1. Given that the secure enclave on devices such as iPhone devices, I'm not sure on Android what curve they're using for its biometric implementations. Isn't there a concern with the, as you mentioned, the randomness of the chosen parameters of R1 curve? So could it be the case that even though you're using the R1 curve to do your signatures on chain or your for on chain transactions, that potentially if there is a backdoor behind that curve, that you're basically handing over your access to any on-chain assets to whoever owns that backdoor? Is that a concern? Is that a valid concern?
Yes, absolutely. That's the conspiracy side, which I briefly mentioned earlier. So because a lot of people are not comfortable with this curve because it is rumored, at least, that's because this is devised by, I think, either NIST or NSA. Yeah, some people claim it has some kind of a, backdoor built in because so far nobody can explain scientifically why these two numbers are chosen. How are they random? So that's a vulnerability to say the least. But here's my thought, right? Because if you people are already using this, right, for the encryption and the signature when they are doing existing apps. So this app, the only thing I think is more vulnerable is because it directly locks up your own chain asset with like a Bitcoin or some kind of tokens, right? So that's only a big. Here's the thing, right? If you're using the latest iPhone or the Android, you are already using this curve. Okay. So if you're really paranoid about it, you can even, I don't know, find some other phones that can use even a different curve. Okay. So that would be my take. So here's the bottom line: you are already using this curve, whether you're aware of it or not, right? So this is still billions of people have used it. So far nobody has proven it's been cracked or there's a backdoor. Yeah, but of course in theory that's a vulnerability for this scheme. Okay. If you're really worried about that kind of attack, a state-sponsored attack, and I don't think this kind of individual hacker is going to crack this, for sure. Okay. Does this kind of answer your question?
That's a good point. Yeah.
Yeah.
That's clear.
Yeah.
In summary, it's more of what you're attacking. Yeah. Thanks.
Mm-hmm. Yeah. Great question. Yeah. For people who have want to, just go into the rabbit hole, just search for this and say this curve is quite a rabbit hole. Yeah, I haven't reached the bottom. Maybe somebody can come back and tell us more. Okay, all right, that's fair enough. Any other questions? If not, let's go to the final one, application of elliptic curves. Okay, so the last one I want to check, is this called encryption. We talk about, all the previous slides is about, cryptography, usually either about encryption or about digital signature, right? So we covered a lot of signatures before. Let's talk about encryption. So, okay, I'm talking about here, maybe this is a little bit of advanced. It's called ElGamal Encryption. So anybody heard about this term before, ElGamal? It's basically an inventor. Okay. Yeah. Don't worry about it. I think it's if I explain it should be simple. Okay. So if not heard about ElGamal, so anybody who heard about the Diffie-Hellman key exchange, which I'm showing here on the left, Diffie-Hellman, also named about after the inventors. Okay, great. So just for people who have not heard about it, let's quickly go review. So basically, it's again as using elliptic curve, you can have a private key. Alice and Bob each have a private key, and then each also has a corresponding public key. Okay, here I show it here. So what they do is they exchange the public key, and then they can derive some shared secret, which only Alice and Bob knows. Okay, and the amazing thing here is about the common secret is anybody who can eavesdrop, who can listen, intercept this communication channel, this kind of attackers, they don't know what the common secret is, right? So this is the most amazing thing about this key exchange, right? So exchange only the public key part. So anybody, attacker, they can capture this, and they don't know what the final thing is. Okay, so using elliptic curve, you can easily see why this is the case, right? So for example, this is a public key, Alice, QA, he shares to Bob, and then how do they derive the shared secret? They just, once they get the Alice public key, Bob just multiplied it with his own private key, right? This is scalar, and this is a point, right? So you got this number. Same, vice versa, right? Bob, Alice does the same thing. Once he gets the public key from Bob, he times his private key with this point, right? So if you do the elliptical math, you can break it down, and you can find out these two give you the same result, right? Because it's just this number, okay? This point. So this is the very basic primitive in cryptography called the elliptical Diffie-Hellman key exchange. Okay, so anybody who's watching the channel, open channel, they can only know QA and QB because they don't know the secret key, right? There's no way they can derive the secret. Make sense so far? Diffie-Hellman?
Yep.
Okay, great. So once we know Diffie-Hellman key exchange, then the ElGamal encryption actually is very easy. It's a slight modification of an extension based on the elliptic curve. Okay. So how does this work? So here, let's say, Bob wants to send a message to Alice. Okay. What does he do? He can, generate again. He can create a random. This is like a random key. K basically it's like a nonce, right? If you know about the ECD signature, he can generate a random value called K, like a nonce. And then what does he do? He do this. He's encrypted in this way. So Alice, right? This is Alice private key and public key. Okay. So what does he do? He calculate the capital K, which is just small lowercase k times the you can think of the P. P is like a generator, right? The base point. So he calculates the K, and also he calculates the ciphertext. What is the ciphertext here? Basically, you encrypt the message M, right? You just C is equal to small k times the public key, because Bob, okay, here's the scheme. Bob wants to send a message M and encrypt it using Alice's public key. So he does this. Okay. So once we have the both of this, Bob sends the both K and C to Alice, sorry. Okay. So Alice, this is encryption, right? This on the left, this is encryption. On the right is the decryption. And then how does Alice gets M out of the K and C? He does this. She does S equals AK, and then the plain text M is just C minus S. Okay. So, we are not going to cover the theoretical proof here, but just let you know. Okay, this can work. This works. This is the so-called ElGamal encryption. Okay, so Bob, encrypts the message with Alice public key and then send the ciphertext, out of which Alice can decrypt and get back M using her private key. Okay, so we don't have to worry about all the the mathematical proof here, but on a high level, is this clear? This encryption and decryption?
Yeah, I think so.
Okay. Anyone else? Is that good? Yeah, you can. Yeah, for anybody who's interested, they can check the math offline. Yeah, it works out. Yeah, okay. So the great thing about this is if you can know all the encryption and decryption, they are using only elliptical primitives, right? For example, here, it's a scalar multiplication. You have one multiplication and one addition. Same for here, in multiplication, you have a subtraction. Yeah, subtraction is just the opposite of addition, right? So this is you can do all these operations using our elliptical primitive. Basically, you can code this in a few lines of code. This is actually you can code it, of course. So here I'm just showing one example how do you use ElGamal encryption in a smart contract place. Okay, so let's say again we are getting back to the so-called it's like a bounty, right? So for example, let's say I have some for example I have let's say article or any kind of digital goods, right? I have an article, I have a picture, I have a movie, I have some videos, and then you want to buy it from me using Bitcoin, right? So here's the thing: if I send you the digital goods first, you may not pay me, or vice versa. If you send the Bitcoin to me, I'm a wrong way where I'll give you the digital goods, right? But with the ElGamal encryption, I can say, hey, you can first the seller can say, hey, this is my goods. I encrypted it with this specific key, okay? And then with your I encrypted with this specific key. Yeah, that's it. And then if you pay me, I'm going to give you the decryption key. Okay. So then we have this contract. It's also very simple. So what this does is, hey, you lock up the key. You lock up the key into the in a smart contract, and then the only way that the seller can redeem this is using the correct decryption key because of the scheme here. You can basically you can encrypt the decryption key, and then the only way you encrypt it, right? Then you have the ciphertext which you publish in this contract. So the only way the seller can redeem this is to expose the secret key here and then redeem it. And so using the elliptical math, you can be sure he cannot cheat, right? So this is a perfect example of using, elliptical cryptography to sell digital goods. Okay. So of course, this the final code is very easy. You just import the elliptical base library, and then you do multiplication, and then you do addition. Basically, you are using the ElGamal encryption here. You just make sure you got the right decryption key. Make sense here? Any questions? So what's it? That's a high level what it does. Okay. So you lock up something
on the page. Oh, sorry.
Go ahead.
On the page of the crypt contract, could you mentioned that Alice would have to, if Alice is the one that is decrypting the contract, that Alice would need to expose or reveal her private key in order to spend the output. Is it also possible to construct a contract such that the contract does the encryption that Bob would do with Alice's public key, and the spending condition is that Alice simply provides the unencrypted data as the input to the contract, which then gets encrypted in the same scheme that Bob would do. Basically, the contract's written such that it encrypts that data and then matches the encrypted input to the on-chain encrypted state, and that matches that as a spending condition.
Yes.
And that the reason for
yeah.
doing this would be so that
Mhm.
Alice doesn't reveal, private key.
Yes, I think it's it's a very great alternative. Yeah, again, right here, it's almost like you know, you got two sides of the coin, right? So here, what I show in the example, I just implement the decryption, right? So you are saying, what if I use I implement the encryption part, right? So make sure, hey, whatever the good parameter, the right parameter you give me, the secret is going to be produce the same ciphertext, but I don't, I just, use this. So here in the example, I'm using this, right? I'm showing the decryption part. So you are saying, hey, maybe it's possible. I want to make sure the encryption part is done right. So you can give me the right message and the K, which give me the right ciphertext. Right? Yeah, I think that's also doable. Yeah, great point. You see what I mean? It's like the two sides of the same coin, right? You can either make sure the decryption matches, or what you are proposing, if I understand correct, the encryption matches. Okay. Yeah, great point. Yeah.
Yeah.
Yes, I think it's doable. Yes. But I have to see the difference. Yeah. What do you think are there any different pros and cons you can think of? So you do not expose.
The key is the only pro I could think of. If you're not, Alice isn't exposing the private key in the pay to encrypt version, if we were to call it that. Whereas with pay to decrypt, you do expose the private key, and there I don't see. I guess it really comes down to use case at the end of the day and which one you would want to use, and
Okay. Yeah, great point. And I just want to add one difference. Okay. If you look at the math here, right? I think this one is I think maybe that's the reason I chose to, code the decryption, because it's simpler, because it's basically it's cheaper, meaning smaller script, right? You have one multiplication and one addition, right? I mean, subtraction is like one addition. So here you have 1, 2 multiplication and one addition. And if people who have attended last time, which I should emphasize, the scalar multiplication is usually the most expensive part. It's going to be, orders of magnitude expensive. I mean, in terms of script, than the multiplication. So if there's another benefit of using the decryption, it's just smaller. It's cheaper, smaller size. Right? One multiplication. You see this? Yeah. If you can, that's a technical detail. Yeah.
Yeah. So if you're okay with exposing, say the private key is used once. If the private key is only used once in this scenario, then the pay to decrypt is a more ideal for cost.
Yes. Yeah, you can throw it away. Or maybe sometimes you are using some kind of way that you cannot change the private key for whatever reason. Then you can switch to this one. With the only downside I can tell is it's a little bit, it's like a double the size of script. Okay. Yeah, great question. And any other comments, questions? Yeah, why not you? I mean, you can do the simple experiment, just implement this, and then to see, just make sure if the toy example, you can publish some ciphertext, and then you expose the original message, and then the K to make sure you can redeem it. Yeah, this could be a good exercise, I think. Yeah, previously we only did decryption. If you could also somebody try the encryption side as well. It's also, I think it's a couple lines. Yeah, because pretty much one elliptic curve operation is just one line. Right? Just what you say here. Because decryption is just one application, one multiplication, and one addition. Okay. Anything else? Okay, that sounds great. And this hopefully give you some idea why I think I'm very, we spend a lot of time to create and optimize at the same time all the elliptic curve cryptography primitives, because yeah, it's a very basic tools, and then upon which you can build a lot of very interesting use cases. We just showed quite a few, right? So this is just the beginning, and you can, this is because this is also just fundamental tools. You can use this very simple primitive to build all kinds of other cryptography, and upon which you can build all kinds of different apps, right? So pay to decrypt, using secure enclaves, a different signature scheme, alternative digital scheme like a ring signature, Robin or Schnorr, or even ECDSA, but for arbitrary data. You can implement all kinds of very innovative use cases, I can tell. Yeah. Okay, any final comments before we wrap up this week?
No, thanks.
Okay, that sounds good.
Great presentation. I had one question. First, sorry. Yeah, I had one question as far as the weekly schedule. Is there a planned set of things we're discussing each week? First time here, so hello everyone. I was just wondering, is there a I'm thinking itinerary, but that's not the word. For next week and the following weeks that are already planned, or is there a place where we can suggest certain topics and maybe what sort of things that we're interested in learning about Escrow?
Yeah, great question. So we publish, okay, just let if you're new here, we will publish this on our YouTube channel.
Mm-hmm.
So there we have a series called Become Smart Contracts. So basically at the beginning, I'm teaching you just step by step how to write one, how to test, how to deploy, all the basic stuff. And things, I think a couple weeks ago, because we finished all the basics, and now you can build your own, so-called decentralized app powered by Escrow. So we kind of switch the topics a little bit, because once we have all the basic covered, and for now we are working through the different use cases. Okay, since about I think couple weeks ago. So as you said, we are more than welcome to have user feedbacks on what kind of topics they're interested in. So you guys suggest, we are on Slack, on Discord, so you can anytime you got interesting things you want us to cover, yeah, please feel free to suggest that, and we'll take it into consideration. Okay, and in terms of like agenda or syllabus, right now we are just walking through the examples. So it's a little bit of ad hoc. Basically, it's just I'm almost ranking it based on the, let's say, the possibility of being used in a real smart contract, in real world smart contract. That's the way I put it. But if you have specific things you are interested in, please suggest in the Discord or Slack. That'd be great.
Okay. Oh, great. Thank you.
Mm-hmm. Thank you. All right. Any other comments? Chris?
Hi, Xiaowei. This is Samir.
Samir. Okay.
I was just wondering, in the last comment about like real world use cases of the smart contracts, like do we do workshops, or how are we doing, trying to solve, like real, because this right now most of the classes are just basic how to get the smart contracts ready, and and so forth, but like in terms of getting the real world use cases, how are we tackling that problem right now through these sessions?
Oh, this is what this session is about, right? So for us, it's always about education, right? Because, it's one thing, people know all about this, and then that they have yet to incorporate this into the amazing app. That's one thing, right? And the reality, I feel for now, because again, for a lot of reasons, it's just a lot of people, they simply don't know what the capabilities are. So for this session, so I'm mostly to at least let people in the community or whoever, even outside of the community, know what kind of things that's possible. You know, for example, there's pay-to decryption or there's a secure enclave, right? It's not. I think it's going to be easily integrated with and practical for a lot of apps. But the problem is, many people simply either don't know about this or they don't know how to implement it. So here I'm trying to just spread the knowledge, and hopefully whoever you guys know, either you guys or some guys you know, or somebody who's watching this on offline, they can take these ideas and actually build products out of it. Does this make sense? So here is all about education, outreach.
Yep, thank you.
Good question. Anything else? Okay, if not,
Yeah,
I will
if
hope.
there's
Okay, go ahead.
yeah, if there's anyone
Yes.
here, available to join the London Blockchain Conference this coming May 31 to June 2, me, myself, and Xiaowei will be joining the event, right, Xiaowei?
Yeah, definitely. I think the Domingo is also
Yeah,
going,
it's
right?
a great time as well
Last time we
to meet
checked.
the guys.
Yeah.
Oh, finally,
Yeah.
I'm going to meet them.
Yeah.
Yeah. Okay, cool. Thank you so much
Oh,
for another
okay,
great
thank you.
time with
All right, thanks for coming. Stay up late. All right, and hopefully I'll see you next week. All right, have a good week. Have a good week, everybody. Bye bye.
Thanks. You too.
Bye.
Thank you.
Thank
Bye
you.
bye. Thank you. Bye bye.